Okay, so we're going to finish up our treatment of Lagrange's equations of motion by looking at the Hamiltonian function, which will give rise to Hamilton's equations. Well, let's redo that. F-U-N-C-T-I-O-N. There we go. So we've seen before that if a generalized coordinate qi is ignorable, then its conjugate generalized momentum pi was a conserved quantity. Now, I mentioned before that that was an application of Nether's theorem. Her theorem is much more general. With application to classical mechanics, it states that if the Lagrangian is symmetric with respect to some variable, in other words, that variable is ignorable, then the conjugate to that variable is conserved. So in other words, we don't have to just look at the generalized coordinates. So we're going to be taking a look at what happens if t is ignorable. Now, before we go on, I should point out that her theorem is an incredibly general thing. Basically, she proved that for pretty much any formulation of anything that could remotely seem to be physics, she showed that if there was asymmetry, there had to be a corresponding conservation law. So, for instance, you can get that electric charge is conserved because there is a symmetry of gauge in the electric potential. You're free to choose a gauge in the electric potential. So that gauge invariance gives rise to electric charge conservation. And similar things happen in when people are working on the standard model. They find a symmetry, then they look for the corresponding conservation law. So, for instance, the laws of physics don't care what direction you're looking, therefore angular momentum is conserved. Alright, but anyway, let's go and look specifically at what happens if t is ignorable. So to do that, we need to go back and look at the Lagrangian some more, and specifically we're going to need to differentiate with respect to time. So it'll be equal to sum over I. The total derivative will be sum over I of the partial L partial Q I Qi dot plus sum over I partial L partial Qi dot Qi double dot, right? Yeah. Plus partial L partial T. So yeah, we're just doing chain rule here. So this is dqi dt, dqi dot dt, partial L partial T. All right. Now I can look at this much of it right here, and I can recognize that this is d dt of partial L partial Qi dot. So that's d dt of the generalized momentum. So that's pi dot. All right. So with that realization, I can rewrite, so that's an aside there, I can rewrite dl dt as sum over I pi dot qi dot plus pi qi double dot plus partial L partial T. This I can look at and recognize that this is a time derivative. This is the time derivative of the sum over I of pi qi dot plus partial L partial T. All right. So here's the trick. If t is ignorable, so that's our big assumption, then we can say that partial L partial t is 0. And that will give us that d dt of L is just d dt of the sum over I pi qi dot. Now, so this is not a general statement. This is only true if t is ignorable. So I can rewrite it a little bit and say d dt of sum over I pi qi dot minus the Lagrangian is equal to 0. So we found our conserved quantity. It's this. So if t is ignorable, the stuff in the square brackets is conserved, so we'll give that a name. And we'll define the Hamiltonian H to be sum over I pi qi dot minus the Lagrangian. All right. So if t is ignorable, and this happens a lot because, one example of t being ignorable, just a little sidebar here, would be, say, if v equals just, if the potential is just a function of position. So this narrow exception is a narrow exception big enough to drive a truck through physics-wise. So if t is ignorable, the Hamiltonian, the Hamiltonian is conserved. Now, let's go and take a look at, go a little further. If the xi's, so these are our Cartesian coordinates, depend only on the generalized coordinates, so the qj's, but not t. So not time. Then I can write my xi dot, it'll be sum over j partial xi partial qj dot. All right. So then the kinetic energy will be sum over I 1/2 mxi dot squared. So that'll be 1/2 sum over j and k of m partial xi partial qj partial xi partial qk qj dot qk dot. Okay. And I lack the motivation, but I'll just assert that you can show that this is equal to pk. Alright, so we get that the kinetic energy is 1/2 sum over I pi qi dot. So again, if t is ignorable for the xi's in terms of the qj's, we can now write our Hamiltonian as, which was sum over I pi qi dot minus L. Well, that will be equal to 2t, because t is half of this, minus Lagrangian is t minus v. So we get that the Hamiltonian is t plus v. So we need t ignorable for the xi's. Well, actually, and the Lagrangian. So pay some attention here. This is an important condition. It's not often that you'll run into it, but at the end of this video, I'll give a cautionary tale that shows what happens if you don't pay careful enough attention to that. So, this is not in general true. Safest is always to go back to here. Find your generalized momentum, find your Lagrangian, just do it right. So if everything's very well behaved, so t is ignorable in the Lagrangian, and the transformation between Cartesian coordinates and your generalized coordinates doesn't have a time dependence, then we can interpret the Hamiltonian as the total mechanical energy. But it isn't always the total mechanical energy, it just is in this case. Alright, so let's go and take a look at a variation, doing variations in the Hamiltonian. So now this is general. Variation of the Hamiltonian be sum over I pi variation the qi dot plus qi dot variation the pi minus partial L partial qi dot partial variation of the qi dot minus partial L partial qi variation of the qi. Alright, so this bit right here is just pi. So because that's pi, those two terms cancel. That's good. So it's also true, though, that's got to be equal, oops. It's also true it's got to be equal to sum over I times partial h partial pi times the variation pi plus partial h partial qi times the variation the qi. Well, I think we've gone ahead and identified our correspondences here, right? So we will compare those terms. Now this guy right here, from Lagrange's equations, this term right here, we can interpret as pi dot. Alright, so comparing the terms, what we get are Hamilton's canonical equations of motion. They say partial h partial pi equals qi dot, and partial h partial qi equals minus pi dot. So basically you got a choice. You can either have n second-order differential equations from Lagrange, or you can have 2n first-order differential equations from Hamilton. Take your pick, but it turns out that for virtually any problem that you'll ever do in classical mechanics, you may as well just go straight to Lagrange, because I'll do a couple examples just to show it. You're going to find that you've just done a more complicated version of getting the right, getting Lagrange's equations at the end of the day. So our first example will be that simple harmonic motion along the cylinder that we did in the previous video. So, or 2 videos ago, sorry. So there what we had was, we'd already worked out that p theta was equal to partial L partial theta. We got that that was mr squared theta dot, and that pz was equal to mz dot. So our Hamiltonian is t plus v, so that'll be 1/2 m, and that's because t is ignorable here, so I can go ahead and use that. 1/2 m r squared theta dot squared plus z dot squared plus 1/2 k r squared minus z squared. So the only difference is that we flipped the sign of this, and we now call it the Hamiltonian. But we've got to rewrite this in terms of our canonical momenta. So I look at this and I go, all right, p theta is mr squared theta dot, right? So if I do p theta squared, that'll give me a theta dot squared. So I can rewrite that as p theta squared over 2m r squared plus, now this one here, this is mz dot here, so p squared will be p squared pz squared over 2m plus 1/2, and here I'm just shifting my potential. I'm just going to make the r go away. Whoops, r squared plus z squared. I'm just making wishing the r away with a shift in potential. 1/2 kz squared. There. So I can look at this and I can say this is the angular momentum squared over 2 times the moment of inertia, and this is p squared. This is the linear momentum squared over 2 times the mass, which, you know, is the way that we often write the kinetic energy of something. All right, so now let's go ahead and do Hamilton's equations on this. So we'll do our p theta dot will equal minus partial h partial theta. Well, that's 0, so it's not too useful. And then our other one here will be theta dot equals partial h partial p theta. Okay, that one's going to give me p theta over mr squared. So that tells me that p theta, which equals mr squared theta dot, is a constant. We know that's a constant because it's ignorable, because theta is ignorable. All right, so nothing new there. Then we can say pz dot is minus partial h partial z, that's minus kz, and z dot is partial h partial pz, that's pz over m. All right, so we get that pz is mz dot, and then we can stick that in over there to give me mz double dot equals minus kz, or getting into canonical form, z double dot plus k over m z equals 0. We identify that as our omega squared, and that's just as before. So I guess it's a matter of taste, but there's an awful lot of, we go ahead, basically we just end up rediscovering what our momenta were anyway, and substituting it back into the other thing to get our second order differential equation that the Lagrangian equations gave us. Let's do another example here. Let's go revisit the spherical pendulum. So our bar of soap in a bowl, if you will. And here I'm just going to be a little smarter about and make that my v equals 0 so I don't have to shift my potential later. M said the length of the string was b. Our coordinates are theta, and our azimuth was phi. Alright, so from before, we have t equals 1/2 mb squared theta dot squared plus 1/2 mb squared sine squared theta times phi dot squared. And v was minus mgb cos theta. So I need to find my generalized momenta. So L equals t minus v. So it'll be 1/2 mb squared theta dot squared. So you see, this is the thing. So unless you've got right on your fingertips, really, you just know what the generalized momenta are, you're going to have to figure out the Lagrangian anyway, and you're going to have to play with it. So plus 1/2 mb squared sine squared phi dot squared plus mgb cos theta. Alright, so we can get our p theta, that's going to be equal to partial L partial theta dot, so that's mb squared theta dot, and our p phi be partial L partial phi dot, that'll be mb squared sine squared theta times phi dot. Alright, so t is ignorable in the Lagrangian, so we can go ahead and at least shortcut that and say that h is equal to t plus v. There's that. So that will be the same thing as here, except we're going to be flipping the sign of that. So 1/2 mb squared theta dot squared plus 1/2 mb squared sine squared theta phi dot squared. Oops, my bad. There. Minus mgb cos theta. And then we need to rewrite this in terms of the canonical momenta. So that will work out to be p theta squared over 2mb squared plus p phi squared over 2mb squared sine squared theta minus mgb cos theta. So there you go. So Hamilton's equations become theta dot equals partial h partial p theta, so that will be equal to p theta over mb squared. Phi dot is partial h partial p phi, so that'll be equal to p phi over mb squared sine squared theta. And also, while we're at it here, we look at the Lagrangian, and we see that phi is ignorable. So we can conclude that since p set on p phi is equal to a constant. All right. All right, so then to get our p theta dot is equal to minus partial h partial theta. That'll be equal to p phi squared cos theta over mb squared sine cubed theta minus mgb sine theta. And then finally p phi dot is equal to minus partial h partial phi is 0, so that just told me what I already saw before, that p phi is a constant. All right, so substituting in, I'm left with this guy here. I can say that this guy here will give me that p theta dot is equal to mb squared theta double dot, right? But that's also equal to this stuff here, p phi squared. But p phi we can write, well, yeah, p phi squared cosine theta over mb squared sine cubed theta minus mgb sine theta. And we got to that point before, so then we can just say and then from there. So I've got other examples we could do. But I don't really think that we're going to gain anything by doing them. Certainly, if you're interested, I'm perfectly happy to go over them with you if you ask. But I don't really think that there's anything to be gained. Generally speaking, it doesn't really give you any new computational convenience. It's just a much more long-winded way to get what Lagrange's equations of motion would have given you. The only thing where you can maybe buy a little bit out of it is if you can at least write the p's directly without having to write down the Lagrangian. Maybe that's a little more convenient. So okay, yeah, let's do one example of that. Let's throw a rock. So there's my coordinate system. We're going at v. We know it's going to be a parabola, but hey. So in a case like this, we can just go ahead and directly write the kinetic energy as being px squared over 2m plus py squared over 2m. So we don't have to write the Lagrangian for that. And we can write the potential energy as mgy. And we're pretty darn sure, even though we didn't write the Hamiltonian, the Lagrangian, there's a t, there's a v there, right? There's no t's showing up anywhere. It's ignorable, so we can just go straight to writing h equals t plus v. So then that's px squared over 2m plus py squared over 2m plus mgy. All right, so then we've got that. Let's go ahead and write Hamilton's equations of motion for this. So we have partial h partial px is equal to x dot, right? So that gives me px over m equals x dot. So that gives me px is equal to mx dot. So, which I kind of already knew anyway. That's why I was able to write the p squared over 2m to begin with. And then the other one for x, partial h partial x is equal to minus px dot. So partial h partial x, there's no x, so that's 0 equals minus px dot, but from here that means that this equal to minus mx double dot, so x double dot is equal to 0. Alright, so let's do this with the y, partial h, partial y, partial py is equal to y dot. That's going to give me, let's see, yep, that's going to be py over m is equal to y dot, so we get that py is equal to my dot, as if we didn't know that already. So then we can write partial h partial y is equal to minus py dot. Alright, so we differentiate that with respect to y, we get an mg. So that gives me mg is equal to minus py dot, which will be equal to minus my double dot. So, whoops, not just quite yet. So that will give me that y double dot is equal to minus g. And then we can do all the standard tricks we've done before. So, I don't know. In a case like this, you probably could have just went straight for the jugular and wrote this without having to formally solve for what the p's were. But frankly, if you're pulling out this machinery to begin with, it's probably because it wasn't all so entirely clear what it was. So you're probably going to have to do all this, and I don't know, you're going to end up with a second order differential equation anyway, pretty much almost certainly. Alright, we can do, I got a couple others queued up, but we can talk about those if you want. Alright, I do want to end though with a cautionary tale. Regarding our Hamiltonian. So let's go think about, let's say I have a massless hoop. And I will rotate it about its diameter at angular velocity omega. Now I have a bead of mass m sitting right there. So we can dimension this out. We'll say the radius of the hoop is r, and that will be our pretty obvious generalized coordinate. Now, what's cautionary here is that we've got just the one generalized variable, but this lives in xyz. So my xyz to theta conversion, if you think about it, as this rotates, has an explicit time dependence. Since that explicitly depends on t, in this case, if you were to blithely write h equals t plus v, you would get the wrong answer. It is not equal. Let's go calculate what the Hamiltonian is for this. So we'll have to do it old school and actually compute the Lagrangian first. So t is equal to 1/2 mr squared omega squared sine squared theta. Okay. Plus 1/2, so that's for the part going into the page there, plus 1/2 mr squared theta dot squared. So for the bit in the plane of the page. All right. The potential energy will be minus mgr cos theta. So I'm putting 0 right in the center of the hoop. Probably as good as anything. All right. So now the Lagrangian is t minus v. So it'll be 1/2 mr squared omega squared sine squared theta. Oops. Squared theta plus 1/2 mr squared theta dot squared minus v will mean plus mgr cos theta. Alright, so that's my Lagrangian. Now let's find my generalized momenta so that I can get about trying to write the Hamiltonian. So my p theta will be partial L partial theta dot. That will be mr squared theta dot as before. That's good. So when I start writing my Hamiltonian, I'll make the substitution that theta dot is equal to p theta over mr squared. Alright, and that's all I've got, so I can rewrite my Lagrangian as 1/2 mr squared omega squared sine squared theta plus mgr cos theta plus p theta squared over 2mr squared. Alright, cool. So now we have to do the Hamiltonian right. So if we do the Hamiltonian right, that is going to be p theta theta dot minus L. So from the theta dot we had before, that's going to be p theta squared over mr squared. Now we subtract the Lagrangian. Minus 1/2 mr squared omega squared sine squared theta minus mgr cos theta minus p theta squared over 2mr squared. Alright, so we have a partial cancellation there. What we get is that our Hamiltonian is equal to p theta squared over 2mr squared minus 1/2 mr squared omega squared sine squared theta minus mgr cos theta. So we can look at this and we can recognize that this term right here is the gravitational potential energy, and this is an effective potential. Now remember, effective potentials arise from kinetic energies. So that's where we run awry, is if we just blithely wrote this as t plus v, we wind up getting the sign of our effective potential flipped. Go ahead and add the t plus v. You're going to have a plus there instead of the minus that you should have had. So it's still the case that t is ignorable in the Lagrangian. So t ignorable for the Lagrangian. Therefore, the Hamiltonian is a constant. It's conserved. But the total mechanical energy, E equals T plus V, not conserved. And we have to say that it's not conserved because there's a time dependence in the mapping from Cartesian to generalized coordinate. And the way we interpret this is that as it's bobbing up and down, the hoop is actually doing work on the bead. And it's doing work on the bead in such a way that it's keeping the Hamiltonian a constant, but sometimes it's adding energy to the bead, other times it's taking energy out. So It's always important to remember, if t is ignorable, the thing that is conserved is the Hamiltonian. In many, many, many cases, especially when you're doing quantum mechanics or thermodynamics, you'll then just immediately say, oh, and the Hamiltonian is the total mechanical energy. But the reason why we don't just rewrite all these equations of motion replacing the Hamiltonian with the total mechanical energy is because the Hamiltonian is not equal to the total mechanical energy all the time. You've got to be careful. If you've got time-dependent constraints like we have here, the Hamiltonian is not equal to the total mechanical energy. The constraint forces are doing work. We could figure out what that work was if we felt like doing some Lagrange multipliers. I'll leave that as an extension to you if you're interested, but I'm just putting this out here as a cautionary tale. Okay, so we are approaching so that's it for Lagrangian mechanics. The next lecture series or video series is going to be on the dynamics of oscillating systems to finish the book.